Welcome. Today we will continue with section 3.1. Topics include vector angle formula, parallel and perpendicular test, vector components, parallelogram area. So to start off with the vector angle formulas. What they really are is just a rebranding of the dot skew product theorem. So we're going to have same conditions. We're going to have a V1, V2, and theta is going to be the angle in between them. And we're going to have cosine of theta is equal to V1 dot V2. And we're going to divide by the magnitude of V1 times by the magnitude of V2. Some of you might look at this and go, wait, I could make I could make this be V1 divided by magnitude of V1. I could do this. Because of the homogeneity of dot product. Which I can rewrite this as U1 dot U2. In other words, the cosine of the dot product of the unit vectors is the cosine of theta, of whatever angle is between these unit vectors. So just interesting. We can write down sine theta as V1 skew V2 divided by magnitude of V1 times the magnitude V2. And through the same process, we could think of this as U1 skew U2. So if I have a unit vector, it's just the skew product that gives me the sine of the theta, that is the angle between two vectors. So let's work with an example. We want to find the angle between V1, which is -7, -1, and V2, which is 6 and 8. So we're going to start with a formula and go, all right, we know that the cosine of theta is equal to V1 dot V2 all over V1 magnitude times V2 magnitude. And we can then take the inverse cosine of both sides and get our theta. So we have to first calculate all of this out. So let's first calculate out the dot product. So we have V1 dot V2, and that will be equal to -7 times 6 plus -1 times 8. So this gets us negative 42 plus a negative 8. So that's negative 42 minus 8, which is negative 50. Let me rewrite that down here. So this is equal to negative 50. That's our dot product. Now we can have magnitude of V1 is equal to the square root of negative 7 squared plus negative 1 squared. And that is 49 plus 1, so that's 50. So that's square root of 50. When we reduce this radical, we can pull out a 25, leaving a 2 on the inside, so we get 5 square root 2. We can have the magnitude of V2 is equal to square root 6 squared plus 8 squared, which is equal to 100, which is, so we're going to take square root of 100, which is 10. So now when we find our theta, we have theta being equal to cosine inverse of, we have negative 50 in the top, or in the numerator. And the denominator, we got 10 times 5 square root 2. So 10 and 5 is 50, so that will cancel with the 50, leaving a negative 1 over square root 2 times top and bottom by square root 2 over 2. And so we get cosine inverse of negative square root 2 over 2. We then look at our restricted domain for cosine, that is within the domain of cosine. We look at our range and we find that this is equivalent to 3 pi over 4. So theta is equal to 3 pi over 4. That is our answer. Notice we do not put plus 2 pi n or any of that because we're looking at the angle between these, which is more of a geometric angle, not a, we're not going to spin it around over and over again unless otherwise specified. So just use what you would get is if you just hit it once and we're not twisting the vectors over and over and over again. Okay. So we can now do what is called the parallel and perpendicular test. All right, so what does this do? Well, we've already found, we already had this property here. What this v1 dot v2 equaling 0 and v1 skew v2 equaling 0. This is when the vector is 0. But we're going to expand that and say, well, what if we don't have a 0 vector? What if we get v1 skew v2 and we get this to equal 0? What happens then? Well, we can look at and go, okay, if we have a 0 for our skew, that means that we have the sine of theta is equaling 0. Well, what sign of theta gets us 0? That is, if they're parallel, they're going in the same direction. So this implies parallel. Vectors. What this means that if I say I have a parallel vectors, that means that I have v1 skew v2 equaling 0. And if I have v1 skew v2 equaling 0, that means they're parallel vectors. And this is when v1 is not equal to v2. Or they're not, sorry, this is when they're not equal to 0. Well, if I have v1 dot v2 equaling 0, and again, v1 and v2 are not 0. Because if they're 0, then it's kind of trivial. It doesn't matter. It doesn't matter what I did with them. But what does this mean? Well, we're going to do the same thing and say, okay, v1 dot v2 gets us 0. So their magnitudes don't matter. Again, they don't matter other than the fact that they can't be 0. And when I take the inverse cosine of 0, what gets cosine to equal 0? Well, that is pi over 2. So in other words, this is when they're perpendicular. So I can't emphasize this enough. When they're not 0 and the skew product is 0, parallel vectors. And when my vectors are not 0, but the dot product is 0, then I have perpendicular vectors. So what this means is that I can start to separate my vectors into different components. I have a vector, let's say here is v1. I can split it into two vectors that sum to that v1. And so I can start calling these vectors as component vectors of p and n, and where my n is what's going alongside with a vector and my p is what's going perpendicular to a vector. Now I drew this in a right angle configuration because this is how we can determine a lot of good things from the vector. We can see it being a triangle and have properties there, but we could also view this as just any vector we can still add and get to here and call that vector W. So if I have vector W, there's some way to get to V1 and kind of break it into different component pieces of what's going with this arbitrary vector and what's perpendicular to this arbitrary vector. So what do I mean by this? Well, let's look at the properties and then we'll explore it. So let's do vector components. All right, so with this, if some vector W does not equal 0, then V can be uniquely written as V equals P plus N, where I have two properties that this satisfies. P equals 0 or P is parallel. So instead of saying it's parallel, I'm going to put skew W is equal to 0. And then 2, we have n, vector n is a 0 vector, or vector n is perpendicular to W, or in this case, I'm going to put dot product to W. So if I'm perpendicular, so n is perpendicular or it's 0, P is parallel or it's 0. And let's explore a few properties of this to showcase the usefulness. So our first property is vector P equals the dot product of V with W divided by the dot product of W with itself. And we're going to times this by W. So now this is a scale or a scalar because we have W. This gives us a number. This gives us also a real number. We're just timesing this by W. So we're basically scaling W to be whatever this P is. Because this P again is parallel. So I can think of this as the magnitude of W squared. So I have V dot W over the magnitude of W squared times vector W, which then, if we wanted to think of taking this and applying it here, we can get vector W divided by the magnitude of vector W. We're just going to peel off one of these. And so that's going to give us some unit vector where U is equal to the unit vector of W. Well, then I can do the exact same thing where I now have this, I have this left over. I have V dot, and the other part of this, because I can imagine this as two of these magnitudes, I can attach it to the W due to the homogeneity of the dot product, which gives me my U. So V dot U times vector U, where U is the unit vector of W. We also have B, property B, which is we take the magnitude of a parallel vector plus the magnitude of a perpendicular vector. Well, we square them, and we're going to add and this is equal to v squared. Now, this shouldn't be too surprising because this is a generalized Pythagorean theorem. You might be wondering, well, where is the plus or the minus 2? Well, or 2 times the dot product of these two vectors. Well, these two vectors, since they're perpendicular by nature, by definition, we know that their dot product must be 0. So that term cancels out. So we're left with something reminiscing of the Pythagorean theorem that we're used to. So let's do C. If vector v does not equal the 0 vector, and theta is the angle between v and w, then we have vector p is equal to the magnitude of v times the cosine of theta divided by the magnitude of w times w, which again we can pull this magnitude of w out, and we get magnitude of vector v times the cosine of theta, and this is all times by vector u being the unit vector of w. Now, what we can do from here is that we can generalize this into that this is basically a one directional vector. And so if I was to take the magnitude of this p vector, I get the magnitude of this p. Let me write the magnitude of p is equal to the magnitude of vector v times the absolute value of cosine theta. Essentially, I'm taking the magnitude of both sides, and when I take the magnitude of both sides, this vector is a distance of 1. So I can ignore it because I'm basically timesing by 1. I'm already taking the magnitude of this vector, so the magnitude of the magnitude is still the same. And cosine becomes absolute value because distance is always positive. And we're able to obtain a similar fashion with n. When we take the vector of it, it just becomes the magnitude of v times the absolute value, or sorry, just of sine theta. Okay. And so the reason why that this is of sine theta is, it would be the absolute value of theta. Absolute value of sine theta. Because again, we're taking the magnitude of vector distances will always be positive. Okay. So there are 2 other things I want to discuss briefly about these properties. And that is that we can think of this vector P as the projection of V on the direction of W. Which we're going to denote as projection of some vector of V, not W. So in fancy terms, it's again this. We're going to take this V and we're going to say, how can we split this V into two vectors that form a right turn or a quarter turn and basically a right angle and sum to V in the direction of W. Basically, how can we make a right triangle with the direction of one of the legs being in W? So in a similar fashion, we can note as N as a component of the normal to W, which is why we call it N, because it's the normal vector. It's the vector that is perpendicular to whatever direction we're starting to talk about. So with this, we can now form the parallelogram area. And so if we can think about this from the standpoint of a parallelogram, we have a parallelogram that looks something like this. So what we can do, conceptually speaking, is we can break down this vector, let's call it this one V, this one W. If we have these two vectors, we want to find the components of V. We basically want to find the height of this parallelogram. And I drew this nicely where this was flat, but we can also imagine it being something like this. It's just much more ugly to draw. And now here's my V, here's my W, here's my parallelogram formed by V and W. And again, I'm basically finding just the height of the parallelogram, the width of the parallelogram. I'm going to times them together, much like how we would do if I was to give you a regular parallelogram that you're used to seeing. But how do we do this? Well, we first have to have V and W not be the zero vector. So we first have to have that. And then we're going to say that the area of parallelogram P, I'm going to use capital P, so that's what I'm calling this guy. It's formed by V and W. That will be equal to the absolute value of V skew W, which we can use our properties and go, okay, our skew product, we can rewrite that as the magnitude of V times the magnitude of W times sine of theta. And that is simply by using the formula that we had before. And just just adjusting it. So this sine theta, we can think of it as this is our theta here. What's sine of theta? It is opposite over hypotenuse. So we have this opposite, which is our n vector, because it's perpendicular to w. And when we find that, that is our n vector divided by our, or the magnitude of our n vector divided by the magnitude of our v vector. So that cancels out with our v vector, leaving us with the magnitude of vector n times the magnitude of vector w, which is essentially height times width. So that's all that really is. But let's work a quick example on that. So we want to find the area of the parallelogram formed by V is equal to 3, 2, and W is equal to -2, -8. So we're just going to find the absolute value of V skew W, which is equal to the absolute value of 3 times -8, because I'm going to take x1 times y2 minus y2, or y2 times x1, 2. Take the absolute value of that, and we're going to have -24 plus 4, absolute value, which is equal to absolute value of -20, which is equal to 20 units squared as the area. So the last little thing that we can do about this is we found the area of parallelogram. Well, what if we took this parallelogram and cut it in half? We now have a triangle that has half the area. So here's my W, here's my V. I cut that in half. That's exactly half of the parallelogram. So the parallelogram formula, which is just this, divided by 2, is the area of a triangle. So in other words, area of some triangle T is equal to 1/2 times V skew W. And that is formula for that. For your check on learning for this video, write down the parallelogram area formula and the triangle area formula. Thank you and have a great day.